So in 1927, two men named Davison and Germer were doing a fairly mundane experiment where they were sending an electron beam against a piece of nickel. And mostly they just wanted to show that no matter how smooth they made the nickel, they would always get diffuse reflection. They would never get specular reflection. After a laboratory accident that messed up their sample, they went to great lengths to fix it. And in the process, they accidentally made the nickel crystals much larger, so that they were larger than the electron beam. The result was that when they sent the beam in, they got a maximum at a very non-specular and non-diffuse direction. In other words, they sent the electron beam straight in this way, and they got a maximum some 50 degrees off to the side. Specular reflection would just go straight back, diffuse would go everywhere. This is exactly the type of thing you would expect in Bragg diffraction that we studied before. In fact, if we redo the experiment, as we would do a Bragg diffraction experiment, for Bragg diffraction we would send in X-rays to a target, for example aluminum crystals, and we would get circular diffraction rings from those X-rays reflecting off of planes within the crystalline structure. Remember, it reflects off the planes, and we get interference between these two beams. And this is what we see for X-rays. Now, if we repeat the experiment using electrons of a single energy, we get this. Notice it's geometrically identical. There's a little bit of difference in some of the intensity and the way it interacts with the photographic plate, but we're getting the exact same diffraction pattern. In other words, not only do photons act like particles, but things we're used to considering particles, such as electrons, can act like waves and exhibit diffraction patterns. Davison, along with G.P. Thomson, the son of J.J. Thomson who discovered the electron, won the Nobel Prize for this experiment. The explanation had actually come somewhat earlier by de Broglie, who had really been trying to explain the spectrum of the hydrogen atom, and we'll talk about that later. But he had suggested that particles have a wavelength equal to Planck's constant over the momentum, which is exactly the same relationship we use for the momentum of a photon. Momentum of a photon is Planck's constant over the wavelength. If we switch wavelength and momentum, we get the de Broglie relationship.